the flow through the water. I put a little drip on the end of my finger and insert the tube into that, and you can see the size of the bubble that it's blowing. And how quickly it inflates something to a size much, much larger than would ever fit in the ear canal. And you can see the breathable nature of the membranes. And it's coming through the part that's gathered because there's much more material being bunched up there for it to breathe through. It'll also breathe through the other side of the bubble if that is closest to the surface. Here's a penny. Now let's see, you can see that the breathability of it deflating slowly and then lifting the quarter again. Now this bubble is only much, much larger than anything that we would put in the ear canal. The most this valve assembly will do is about 2.8 kilopascals, which is far, far greater than is needed in the ear. Optimum inflation pressures for the ear are 100 pascals to 500. Something in that range. Now let's show the work that this bubble is doing at optimum pressure here for this valve assembly. Now I'm having to squeeze this with some force. The surround for the membranes comes right out to where the miniature bolts are located. And you can see that it inflates and deflates at a commensurate rate. Deflation, inflation, and the pressure that we're generating right now on the micromanometer is 1.7 kilopascals. Finally got the quarter so it's not falling off. Can you see that? Now the size of this valve, this much of it is just the chassis, and this much would be the valve. This is a valve that's sealed in epoxy. And I can tell you that we can get it much smaller than that quite easily.